Hello, we are Team 4 and our project is about crowd-aware robot navigation with attention-based deep reinforcement learning. We will first introduce the paper we chose in our original plan. We will then discuss about our progress so far, which will include the problems we encountered, and finish with our modifications to our improvement plan. So a little background, the use of robots within pedestrian spaces is becoming increasingly more common, with robots having been successful in bringing more convenience into our lives. It is still challenging to create robots that are socially aware. For example, mobile robots should be able to get around in a crowded environment in an effective and socially compliant manner, meaning they should be aware of how humans to walk in a crowd in order to avoid collision or making the human have to modify their behavior. So the paper we chose is Crowd-Robot Interaction, Crowd-Aware Robot Navigation with Attention-Based Deep Reinforcement Learning. Prior works tend to frame the problem as a one-way human-robot interaction problem. The goal of this work was to explore the problem by looking at a crowd as a whole and exploring the concept of crowd-robot interaction more deeply, and to design a model that can allow for socially compliant navigation. The claimed contributions of the paper were a self-attention mechanism that learns the collective importance of neighboring humans with respect to future states, being able to jointly model human-robot and human-human interaction in the RL framework, and a model that can anticipate crowd dynamics and navigate in time efficient paths outperforming state-of-the-art methods. So this paper had a network consisting of three modules, the interaction module, pooling module, and planning module. So first is the interaction module. This module explicitly models the human-robot interaction while using local maps as a coarse grain representation for the human-human interactions. The state of the human in the map tensor is embedded with the state of the robot into a fixed length vector using a multi-layer perceptron to extract the pairwise interaction feature between the robot and each human. Next is the pooling module. Interaction between the robot and each human are extracted from the interaction module and subsequently aggregated in the pooling module. The pooling module uses a multi-layer perceptron to compute the attention score for each person from the individual embedding vector together with the mean embedding vector. The purpose of this module is to learn the collective importance of neighboring humans with respect to future states. Finally is the planning module. This estimates the value of the joint state of the human and the robot and humans for navigation in crowds. Based on the compact representation of the crowd, it estimates the state value for cooperative planning. The simulations conducted use circle crossing scenarios where the human agents were trained with Orca. All the humans were randomly placed on a circle of a radius of 4 meters, and their goal positions were on the opposite side of the circle. To evaluate, they implemented 3 state-of-the-art methods to use as a baseline. Next, I'll talk about our reproduction and improvement plans. The paper source code is available in GitHub, and we refer to that for our implementation. And our improvement plan has 2 main components. First, we want to add more real-world scenarios. Some examples include static objects, increasing crowd density, and adjusting the size of the environment to simulate more narrow places like hallways. Additionally, we would like to introduce more natural human movements. This paper used ORCA to train the humans. ORCA stands for Optimal Reciprocal Collision Avoidance, and so it avoids collision by letting each agent take half of the responsibility. But in real-world scenarios, people have many different strategies when navigating crowded areas, so we want to reflect this more accurately.
From now on, I will share about our progress and some problems we observed. We used the specification listed to implement the code. We used the source code from GitHub repo as a baseline and trained the model with circular crossing cases. It takes 9 hours to train 10,000 episodes with our CPU. The visualization of our one test case is shown in the right. We compared our replica model with the paper's one. Due to time, we only tested with Orca and SARL with the same parameter setting. We found that our results were somewhat comparable to the results found in the paper. In the SARL case, our model actually being slightly faster with a high reward than the paper. The total cumulative discounted reward is also comparable to the papers. Our result is on the left, and on the right in orange is paper's SARL result. To make a progress and observation, we try to make more realistic scenarios as mentioned in our implementation plan. We created simulations that include both static and moving objects that the robot would have to navigate around. On the right, you can see the current results from our implementation of this. For each case, a random number of human agents are chosen and set to start at their goal position to make them stop. The performance decreased significantly with a success rate of only 64% with 178 timeout cases. Additionally, while reading our paper, we thought it was interesting that the authors claimed that their solution could handle n human agents, but all of their training and testing were conducted with only 5 humans. And so we were curious to compare the difference as the number of agents is increased. In other words, replicating more of a crowd dynamic. We initially thought that there would be some failed cases because the environment is changed, but it gives almost same result with slower time and 3 timeout cases. Also, we found that the model trained with 10 humans can still success to the cases with 5 humans. We observed that changing the number of humans doesn't affect the success ratio, so we started to focus more on the obstacle cases instead. Next, we will discuss some problems we encountered. During our initial experiments, we noticed an issue that wasn't mentioned in the paper, the freezing robot problem. This is a well-known problem that can occur that causes the robot to not reach the goal. Timeout cases are highly related to this. This usually happens in more challenging situations that cause the robot to be unable to make a decision, which causes it to freeze completely or get stuck in a loop, like how you can see on the right. While we noticed this rarely in the original implementation, as we change the situations by adding more humans, adding static objects, or changing the size of the simulation has caused this problem to happen often. We will try to figure out why this is occur and do some researches to find the possible algorithms to solve. Also, in our current implementation, static objects are created by placing the human agents at their goal to keep them from moving. But as you can see in the GIF, as human 2 approaches the static human 4 moves out of its way to avoid collision. This is because even the static human agents behave like ORCA. We believe that this might be affecting the robot's pathing, and so to combat this issue, we will create a separate static objects agent that isn't trained with a policy. While our implementation, the biggest problem was that the training is CPU intensive. The total training time of the original code is roughly 9 hours. Moreover, as we add our modification, training time increased exponentially. When we trained with 10 human agents, the training time was almost 20 hours. This has made our progress lower than we originally anticipated, as we should retrain with major modifications. To solve this issue, we have been looking into ways to improve the training time. We would like to recreate the code to use GPU acceleration to decrease training time. Luckily, we have found that Isaac Jim from NVIDIA, which is fit for us, so we hope it could help us. To sum up, we are going to present about what we will do some modifications to improve our paper. In addition to our original plan, we decided to add a couple of modifications to address the problems we encountered. As we mentioned, we experienced the freezing robot problem numerous times throughout our current implementation process. We are concerned it may develop into a bigger issue as we continue, and so if necessary, we would like to think of the solution that could combat this. Next, we would like to create a separate static object agent without any policy, which would act like an obstacle. And then finally, if we think it is doable, we work on implementing a GPU-intensive training version, as we believe it could lower the training time significantly. Thank you for listening.